Welcome to the video, which is a continuation of the chain rule, some different kinds of questions which mix up some other types of past exam style questions to do with chain and product and quotient rule, plus a little introduction to higher order derivatives as well. So here we go. Make sure you've got your notes booklet with you. So here are some different types of past exam questions. On the previous pages we've seen some regular kind of exam kind of questions where you're just asked to find the derivative. Product quotient and chain rule, using the product quotient and chain rule. Here's some different style ones that you might also see can possibly pop up on some past exams, or they could, there's one like this in your textbook too, which I do later on as well. I think, yeah, anyway, so continuing on, here's our little example. So you've got a table here, and it says in the table above, the values of f and g, so f and g, and their derivatives, f dash x and g dash x, at x equals 2 and x equals 5 are given. So we're given some values of the original functions, the y values for the original functions, and the derivatives at x equals 2, and the same for at x equals 5. They also state in the question that let h of x, a different function, equal f of x, g of x. So what does that mean? That means f of x times g of x. So you would probably agree with me in saying that h of x is the product of two functions. That's something to be aware of. You've got the product of two functions here. A little hint that there might be a product rule popping up somewhere. So they haven't told us the functions. They've just given us some values of the y values at the y coordinates at x equals 2 and the derivatives at x equals 2, and same for at x equals 5. So find h of 2. So notice in question B they ask you to find h dash of 5. That's the derivative. But h of 2 is a nice simple one. H of 2 just means sub in 2 into h of x. So if you subbed in 2 into h of x, it's like f of 2, g of 2. Or you might prefer to write that up. H of 2 therefore is f of 2 times g of 2. You don't need to put the times there, but if it's confusing you to write f brackets 2, g brackets 2, you could write it like this instead, put a multiply sign there. So notice that f of 2 and g of 2 you can just get from the table above, because f of x at x equals 2, that is f of 2, so f of 2 is 1, and g of 2 is just the value of g of x at x equals 2, not at 5, because they're saying h of 2. So we're ignoring this one, we're just dealing with this row here, when x is 2. So h of 2 is f of 2 times g of 2. So f of 2 is 1, g of 2 is 4. So just show that you times those two together, and the answer of h of 2 is just 4. So that's just basic substitution and reading the correct numbers from the table, basically. A little bit more complicated if they say find h dash of 5. So notice h dash of 5, so we're dealing with this one here, h dash of 5 instead here. So here we go, h dash of 5. So they mean the derivative of h of x, but at x equals 5, if you subbed in 5 into that. So remember, h of x is a product of two functions, so to find h dash of x, we have to use the product rule. So just reminding you that the product rule, here's the whole thing answered, the product rule, remember, is u dash v plus v dash u. So first of all, let's state what u is. So u is the first function, which according to this one, that's u, f of x is u, and g of x can be v, so because it's u times v. So let's state that. U is f of x, v is g of x. And from the table above, they're saying at 5 this time, at h equals 5. So what's f of x at 5, at x equals 5, and g of x at x equals 5? Let's see, we got that from here. So f of x is 9 at x equals 5, and g of x is, g of 5 is negative 2. So that's what I've popped in here. I've just popped in what those actual numbers are. And remember, for the product and quotient rule, we also need to say what is u dash and v dash. So u dash, of course, is just the derivative of u. So the derivative of u is just f dash x, of course. And v dash is the derivative of v. So in this case, the derivative of this is g dash of x. So notice it's still at x equals 5, so find out what is f dash of 5 and what is g dash of 5 from the table above. Let's go back up. F dash, make sure you don't read from here by mistake, f dash 5, so f of the derivative at x equals 5 is 1, and the derivative at x equals of g of x at x equals 5 is 2, so 1 and 2. So that's important to kind of like write them all out. So remember, and then we can just sub these numbers into the product rule. So h dash of x equals u dash v plus v dash u dash is 1, v is -2, so 1 times -2, plus v dash is 2, u is 9, so 2 brackets 9, 1 times -2 is -2, 2 times 9 is 18, -2 plus 18, 16. Yay, so that's done. So the derivative at x equals 5 of that that product of f of x, g of x, is 16. So positive gradient, if you were asked. So it's a positive gradient. Let's try another similar one on the next page, but if you're given the quotient rule instead. Similar kind of setup. So I've got a similar example. In the table above, the values of f and g and their derivatives are given at x equals 6 and x equals 1. But this time they're saying let h of x equal f of x divided by g of x. Remember on the previous one it was f of x times g of x, so that was the product of two functions. This time we've got the quotient of two functions. So it means if we're dealing with a derivative, we need to use the quotient rule instead, which we asked for a derivative down there. So in A though, we're just asked to find h of 1. So h of 1 is just f of 1 divided by g of 1. So let's write that. H of 1 is just f of 1 divided by g of 1. No derivatives required here. From the table, f of 1. So make sure you don't read from the row for 6 instead. We're talking about x being 1. So we should be reading from the second row where x is 1. So f of 1, f of x at x equals 1 is just 4. And g of 1 is g of x at x equals 1, -1. So write 4 divided by -1, and just work out that answer. Positive divided by a negative is a negative. So notice I'm putting in extra points. These values came from the table above, just in case you might want to write that too, in case you look back on this and think, where on earth did I get those two numbers from? The next question, a bit more work because it's derivative. So find h dash of 6. So it means find the derivative of h of x at x equals 6. That's what it's asking. So this time we're going to be dealing with the numbers from the top row. So notice I reversed it this time, not the first row and then the second row. We do the second row first and then the first row in part B instead. So as h of x, see h of x is f of x divided by g of x. So making a little note for myself here. As h of x is the quotient of two functions, we either use, instead of the product rule, we're going to use the quotient rule instead to find the derivative. Just checking it's still recording. Good, yep it is. So to use the quotient rule, remember h dash of x, u dash v minus v dash u over v squared. So maybe I might write that over the side first. I need to define what these things are. U is always the function that's in the numerator. So the numerator is f of x. And v has to be the denominator, which is g of x. So at x equals 6, what's f of 6 and g of 6? And that's how I got those two numbers. Let's see. For 6, f of 6 is 5, and g of 6 is 3. So that's where the 5 and the 3 come from. 5 and 3. We also need the derivatives, u dash and v dash. U dash, so the derivative of f of x is, of course, f dash x, and the derivative of g of x is, of course, g dash x. So at x equals 6, what are these two values? From the table, f dash x at x equals 6 is just -2. G dash x at x equals 6 is 7. So write those out, -2 and 7. Then plug them into your lovely little quotient rule. And notice I made a point, in case you forget in future months or something and you want to look back on these notes. These values in black came from the table above. You might forget that in a few months' time. So we've got u dash v, u dash v. U dash v is -2 times 3. Minus, write in the minus so you don't forget, v dash u. V dash u is 7 times 5. All over v squared. Don't forget so v, just be really careful, v is 3. So see, having them written out here really helps you to sub in the correct numbers, having them written out like this. And then don't forget to divide by v squared, that's a common thing. Sometimes people forget the minus in the product rule too. So we've got -2 times 3 is -6. Subtract 7 times 5 is 35. Divided by 3 squared is 9. What's minus 6 take away 35? It's negative 41 over 9, and that doesn't simplify. So the derivative of h of x at x equals 6 is negative 41 over 9. So the gradient at x equals 6 is of this function at h of x is in negative gradient, so it's decreasing. Great. A little bit trickier if we have composite functions. So remember, when we deal with composite functions, we use the chain rule. So again, we've got this one comes from the textbook, the Oxford textbook, exercise 7L, question 14, page 219. So here we've got in the table above, we've got some numbers, x equals 3 at x equals 4. We've got f of x, g of x, f dash x, g of x again. So in the table above, the values of f and g and their derivatives at x equals 3 and x equals 4 are given. A, find the gradient of the composite function when x equals 3. If we knew what the two functions were, we could find the composite function, find its derivative, and then sub in x is 3. That would be great. But they didn't give us any functions, just like before. They just instead just gave us the numbers that would be the result when you sub them into the functions. So that's a bit harder. So this is a composite function. We use a chain rule when there is a composite function. So if you're asked to find a derivative, which you are in this case, find the gradient, because it's not just asking for h of x, it's asking for the gradient. So it's a derivative of f of g of x. So remember, f, that's kind of that particular kind of notation. F of g of x means g of x was subbed into f. So it's important to identify what's the mother function. So the parent function is f, and the baby function, if you're going to use that word, baby function, the one that was subbed in would have been g of x. So when I do my chain rule, I tend to do that. I tend to define what is the baby. The one that was subbed in, the baby, was g of x. So therefore, of course, its derivative would be just g dash of x. And at x equals 3, g dash of 3, let's get that from the table above, because this question's saying at x equals 3. So g dash of 3, g dash of x at x equals 3 is 2. That's where this 2 came from. So I identified the baby function, first of all, g of x. Its derivative, of course, will be g dash of x. And x equals 3 will be g dash of 3, so 2. And the parent function will be f of u. So f of u, because u is g of x. And so f of u is, its derivative, of course, will just be f dash u. And notice what's tricky about this one is, so u, what they mean by why I've subbed in 4 here instead is because at x equals 3, what is the value of u is what I'm trying to work out. So at x equals 3, what's the value of u? So I got that from the table above. So at x equals 3, u is g of x, so at x equals 3, there must be g of 3. And I went to the table above, so g of 3 is 4. So that's what I've done here. It's a little bit more complicated. That's why I did this bit here. It's to help me out with this part here. So g of 3 is 4, so f dash u is asking for f of 4, because the u value, the value of u at x equals 3 is 4. So instead we're finding f dash of 4, which is a bit more tricky. So f dash of 4 is 3. So f dash of, you can just notice it happened to be that 4 is in the table as well. It was a nice coincidence. So f dash of 4 is 3, and the question was set up to be the case. So f dash of 4 is 3, and so we've found f of u. Once we subbed in the value u at x equals 3, that's f dash of 4, which from the table is 3. So then you times those two things together, times the derivative of the baby by the derivative of the parent with u subbed in, is how you get your answer. So 2, because remember we have to sub in u in order before we get a final answer. 2 times 3, I just wrote it out here, 2 times 3. So the gradient of the composite function when x is 3 is 6, so it's a positive gradient. Okay, similar one. Find the gradient of 1 over g of x squared. So it's a chain rule one again, because we've got a function within a function. It's not a quotient rule because we don't have a function over a function. Instead we just have 1 over with like a parent function could be 1 over u squared, and the baby function would be g of x. Because it's not like there's like 3x over g of x squared. Then that would be kind of like a quotient rule kind of style one. So we use a chain rule when there is a composite function. And this time it's asking for x equals 4. X equals 4. Beforehand it was asking at x equals 3. So chain rule, we've got to identify the baby function and the parent function. I do that. So the one that baby function is the one that was subbed in. The one that was subbed in clearly is g of x. And the parent function, so u, I call the baby function, the parent function would be 1 over u squared. So baby function is g of x. Parent function is 1 over u squared, which could also be written as u to the minus 2. So derivative of the baby function is what we need. We need the derivative of the parent function when we times those two together. So the derivative of the baby function would, if baby is g of x, then the derivative of the baby function would be g dash of x. And they say at x equals 4. So g dash of 4, let's get that from the table. G dash of 4 is just 4. That's where the 4 comes from. So you might want to make a note of that. I kind of was running out of space here, but you might want to make a note of where this number came from. I read these two numbers came from the table above. Well, actually, kind of. This one did anyway. So g dash 4, according to the table above, is 4. So we found the derivative of the baby function. Now the parent function, remember, was 1 over u squared. So we've got to find the derivative of that. So to find the derivative of 1 over u squared, first of all, express the parent function, or flatten it out first. So we've got 1 over u squared is the same as u to the power of negative 2, or 1u to the power of negative 2. What's the derivative of this? It will be minus 2u, subtract 1 to the negative 3. So the derivative of the parent function is minus 2, because you multiply minus 2 by 1. U, and subtract 1 from the exponent, is negative 3. Again, we've now got to sub in what u is. So you could put u in red if you want. Let's do that, just so you see where is u coming from. Because remember, we've got to sub in what is u at x equals 4. So u at x equals 4 is what I worked out here. So u at x equals 4 is g of 4. And g of 4, g of x at 4 is negative 1. So I found out what the u is at x equals 4. It's negative 1, and then that gets subbed into here for u. So negative 2u to the minus 3 is negative 2 brackets 1 to the minus 3. If it's with calculator, you can just work out that number, plug it in like that. If it was non-calc, you should probably express it with positive indices. So if positive indices, that would be negative 2 over negative 1 cubed. Like this, it would be negative 2 over u cubed. So this would be negative 2 over negative 1 in brackets cubed. And which we can work out. Negative 2 is negative 2. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1. Negative 2 divided by negative 1 is positive 2. So we've found the derivative of the baby function at x equals 4. We found the derivative of the parent function at x equals 4. The answer to the chain rule is the product of those two things. You just multiply them together, which I wrote it here. 4 times 2 is 8. So the gradient of this function at x equals 4 is 8. So the chain rule ones were a little bit harder. I personally found them a bit harder than the product and quotient rule ones. Okay, little intro to higher order derivatives. So what notation, just a flashback, what notation do we use to represent the derivative of the function, So let's change that. Hopefully I've fixed it up on yours. So your printout will be right. Of the function. What notation do we use to represent the derivative of the function if in the form of? So I need to erase this. So again, this will probably be fixed up on yours. So what notation do we use to represent the derivative of the function in the form of? So hopefully on yours I fixed it up. In the form of f of x. So the notation, if it's f of x, the notation for the derivative is f dash x, the Newton notation. If it's in the form of y, the derivative is dy dx, the Leibniz notation. Just be aware, if you could use a Newton notation on this too, and it would just be, if you did, it would be y dash, would be the Newton notation of y. But like you know how I go u dash v minus v dash u, that kind of stuff. So that's using Newton notation. But that's those two ways what I was meaning. Higher order derivatives. So you could be asked to find the derivative of these derivatives. This is called the second derivative. So this is called the first derivative, and it's possible to be asked to find the second derivative. If it's a second derivative, we would use the following notation. Second derivative of f of x is f dash dash x, because the derivative is f dash x, so the second derivative is if f with two dashes x. The second derivative of dy dx is a bit trickier to write. You write d squared y over dy squared. Okay, so the second derivative has got some purpose. It can give us useful information about the nature of the stationary point. So this is important to remember. So if the second derivative turns out to be negative, so basically you find out what is the x-coordinate of the stationary point. Like stationary point, I mean a maximum, a minimum, or a point of inflection. So you find out what is the x-coordinate of the stationary point by setting the first derivative equal to 0 and solving for x. If you take that x value and sub it into the second derivative and you get a negative answer, that means the stationary point that you found is a maximum. So maximum, thinking like it's negative, it's frowning. So if that helps you remember. So if it's negative, it's a maximum because it's like a frowning kind of one. If you subbed in the x-coordinate of the stationary point into the second derivative and you got a positive result, then that meant the stationary point was a minimum. So think positive, smiling. That's how I tend to remember it. Negative, second derivative, frowning, positive, smiling. So it's a minimum in that case. If you subbed in the x-coordinate of the stationary point into the second derivative and you got an answer of 0, that means that stationary point was a point of inflection. So points of inflection are kind of like this, like that. The derivative at these points is still just 0 because it's still positive and then stays positive. It's not like it goes positive and then turns negative, but it stays positive, except it hits 0 at this point because see, it's steep, so a high positive, and then it flattens, so it becomes a lower positive. Like it could have been 3 here and then 2 here and then 1 and then 0.9, 0.8, 0.6, and then it cuts through 0, and then it's quite flat still, so it's like 0.1, 0.2, 0.6, then it gets steeper and steeper, like 2, 3, 5, and so on. So as it's getting kind of like a high positive value to a low positive value, it cuts through 0, low positive value to a high positive value. So that's why it's able to be 0 at these points of inflection. So same points of inflection could be going down as well, like that. So that's the important thing. If you sub in the x-coordinate of the stationary point into the second derivative, you get a negative, it's a max. If you sub it into the second derivative, you get a positive, it was a min. If you sub it into the second derivative and you got a 0, answer of 0, the stationary point was a point of inflection. So just a bit more on the notation as well. Similarly, there are also higher order derivatives, such as the third derivative, the fourth derivative, etc. The one that has the most purpose in our course is the second derivative. That's the most important one, where you actually have some applications that you can use, like the points of working out what kind of stationary point it was. But it is possible to be asked for a third, fourth, fifth, and so on derivative. Goes on and on. The notation we would use for these are, if it was a third derivative, second derivative is f dash dash x, third would be f triple dash x, and it would be d3x dx cubed if it was that notation. Fourth derivative, once we get beyond the third derivative, you don't want to be writing a ridiculous amount of dashes, so they just start to put the number 4 here instead. So otherwise you just end up having to write too many dashes, it just gets silly. So they call this prime notation as well. So go f of 4x, similar to the one above though, d4x over dx squared. The fifth derivative, f of 5 of x, d5x over dx5, and so on. So I'll just finish that one up right there.